So before we move to the session, I would like to discuss some interesting facts about cement and concrete. It is estimated that in the year 2023, 4 billion tons of cement was produced. And another important thing is 30 billion tons of concrete was produced out of 4 billion tons of cement. And in the year 2030, the global cement production may reach up to 5 billion tons. This quantity is more than enough to cover the entire Kerala state with 1 inch thick cement. So that much amount of cement is being produced and is being utilized throughout the world. And coming to the next, why concrete is most commonly used building materials and why not others? Actually, based on my perspective as well as from the recent studies led by Professor Ghetto and Professor Manusandan from IIT Madras, there are 5 aspects which covers versatile, durable, constructible, available as well as economical. These are the 5 major aspects in which cement concrete plays a major role. Versatile in the sense, the adaptability. Concrete is also called as liquid stone, which acts as a liquid or plastic mixture when it is wet. Whereas in the liquid state, it can be poured off and can be molded off into any shapes or any sizes or any forms. And once it sets, it acts as a stone. That is why it is called as liquid stone. This allows for the freedom of construction and reduces the structural complexity. Its properties can be altered by adjusting the mixer size. For example, if we alter the water cement ratio, aggregate proportion, and the proportions of admixtures, say for example, plasticizer or retarder or air entering mixtures, the physical mechanical properties as well as the durability properties of the concrete will be varied. That is one of the greatest advantage of using this. And as I said previously, it can be molded into different shapes. Its application in the civil is widespread in all the civil applications. And the second important aspect is durable. Concrete shows good durability characteristics under aggressive conditions such as marine environments, whereas steel and other materials will not do the same activity because of the possibility of corrosion and other related issues in the marine environment. Also, concrete has some disadvantages in offshore application, but when compared to all other construction materials, the longevity of the concrete under such condition is quite high. And if properly designed, the concrete structures may last for centuries. And another important aspect is constructible. Concrete is highly flexible. It can be constructed in on-site as well as off-site based on the requirement. And next is availability. All the concrete mix ingredients were commonly available throughout the world, say for example, sand, aggregates, and water. But in the case of cement, it's quite different. Why? Because cement production depends on country to country, and the proportion, that is the chemical constituents of cement, vary from place to place. Say for example, we are now in the 2nd generation concrete, where Joseph Aspidin was formulated in the year 1824, which is 200 years ago in England. The same concrete was still now used, but in some countries, people are just going to replace some proportion of cement with supplementary cementitious materials. It's called as sustainable concrete. And this type of concrete we call it as 3rd generation concrete. We are just slowly moving from 2nd generation to 3rd generation concrete. And the last aspect is economical. Once the building is constructed with the help of concrete, it can stand for years. So where low maintenance is required when compared to all other construction materials. So if you provide very low maintenance, it can able to last for centuries. So if you can take care of any steel or bamboo based structures, it may tends to fail or degrade under different environmental condition. So this type of failures or degradation cannot be seen in concrete based structures. Apart from these 5 reasons, we have few more things. One is fire resistance and another one is water and wind resistance, whereas steel and other materials will not do so as concrete behaves. And coming to next, concrete might be of less durable under some condition, Generally, concrete is a brittle material. It will not take any tensile loads. Because of it, we are going to use steel as a reinforcing element to take care of the tensile loads. But in addition to that, some of the drawbacks are available in concrete also. Says for example, cracking. Different types of cracks will be there. Says for example, shrinkage cracks. During the setting time, it may happen, and loading cracks due to the application of heavy loads, and durability cracks. It may appear due to different environmental factors. Apart from this, there are many cracks also seen. Says for example, thermal cracks, expansion and contraction cracks. This is due to different weathering conditions. This type of cracks will happen. And the next is freeze and thaw cycles. So countries like cold weather regions have alternate wetting and drying, because of which the water tends to enter through the concrete pores and tends to expand during the cold periods, which creates a pressure inside the concrete matrix, that is in the gel matrix. So as a result of it, cracking will be taking place, and slowly it tends to affect the ITZ, that is interfacial transition zone, and leading to failure of the concrete finally. And last is ductility. As we all know, the concrete is a brittle. It can't able to withstand seismic forces and as well as heavy wind forces. So to accompany that, we have to provide a reinforcing material such as steel or some other low cost materials. And before starting to the life cycle assessment of concrete, I'll place two questions in front of you. How should we evaluate the sustainability aspects of concrete? And second one is how we can mitigate the environmental impacts. So if you find the answers of these questions at the end of this session, then you have completed the initial level of sustainability expert tests. Introduction to life cycle assessment. Generally, life cycle assessment is a methodology or an algorithm or a step-by-step procedure to evaluate the environmental impacts of concrete, how it is affecting the society. So in general, concrete is also just like human beings, where a baby is formed and requires 10 months to face the challenges in the outside world. Similarly, concrete requires 20 days of curing after casting to attain its strength for its intended use. The life of human being is estimated as 75 to 100 years. Similarly, the average lifespan of concrete structure is also estimated to be 75 to 100 years. In simple words, LCA is the history of concrete from birth to death. Then, this slide represents the life cycle assessment of concrete. So we have four pillars of life cycle assessment LCA. First pillar is goal and scope. Second one is inventory analysis, and third one is impact assessment, and fourth one is interpretation. So let's see one by one. First one is goal and scope. This is the first phase, defining what to do, why to do, how to do, and for whom to do. Okay, for the life cycle assessment of concrete. Second one is system boundaries, which life cycle stage and the processes are included or excluded. You have to decide which stage has to be included. Say, for example, in the case of human beings, whether you want information during the childhood days, or else in the case of teenage stage, or else in the stage of senior citizen stage. So similarly, concrete also has to be divided in which stage you have to assess the parameters. Okay, and next is data requirement and quality. Specifies the types of data, primary data as well as secondary data, representing initial stage of emissions or initial stage of requirements, or else a final stage of energy data, or else the carbon data. And that too we can represent in terms of geographical based, or else to a specific location based. Then finally, the limitation. Each and every study has its own limitation. We are human beings. Generally, we do mistakes. Similarly, during casting or else the production of concrete, we often do mistakes. So that mistake has to be considered as the limitation of the life cycle assessment of the concrete. First one, goal. Goal answers three questions: purpose, audience, as well as the applications. Okay, what is the LCA study trying to achieve? Says, for example, whether you want to estimate the carbon emission or the energy requirement or human toxicity or environmental toxicity and so on. And second question is, who will use the results? Whether these results will be utilized by the manufacturers, I mean the concrete manufacturers or RMC plants, engineers, then policymakers such as Bureau of Indian Standards or American Company Institutes, and finally the research community. Then how will the results will be used? Either it is used for marketing purpose, stating that the concrete is sustainable and it can be long lasting like that, and for taking internal decision makings inside the production units, then for getting green building certification and for academic research.